recap the left side that you guys had to do. All right. So first off, who wants to start us off with number 1? So after you did Pythagorean theorem and everything, what'd you get for the 3-3 triangle? Someone raise your hand, tell me what you got after you simplify the radical. Elizabeth. Good. So if you did Pythagorean theorem, I believe you should have gotten like the square root of 18, and then you had to simplify the radical of 3 square root 2. All right. Elizabeth, pick someone to tell me the next one. Good. Pick someone to tell me the last one. Good. Now, again, the reason that I asked you guys to simplify the radicals is because it's pretty obvious what the pattern is. All right, what do you guys think the pattern is? So what do they have in common? What do all 3 of those triangles have in common? Right, it's the leg, one of the legs times the square root of 2. All right, and what do you notice about both legs? They're the same, which means this right triangle is not only a 45, 45, 90, it's also a what? It's an isosceles right triangle. All right, so not only is it a right triangle, it's an isosceles. Right triangle. It's actually the only way that a right triangle can be an isosceles triangle is if 2 angles are 45 degrees and the 2 sides are equal. It's the only way a right triangle can also be an isosceles. All right. Now, what is the ratio of the 2 legs of each triangle? All right, so you literally just had to take the 2 legs, put one over the other. So let's see, Sutton was the last one. So Sutton, pick someone to tell me number 2. So what's the ratio of the 2 legs? 1. So if you do 3 over 3, that's equal to 5 over 5, which is equal to 8 over 8, which is 1. Now, if we calculated the hypotenuse to the leg for each of the triangles, all right, what did you end up getting? So Caitlin, pick someone. Right, so if we did 3 square root of 2 over 3, the 3's would cancel out, we get the square root of 2. 5 square root 2 over 5, 5's cancel out, square root 2. And then 8 square root 2 over 8, cancel, we get the square root of 2. So what we notice, you get square root of 2 for all 3. Now, if we know the hypotenuse of an isosceles right triangle, how do you think we would find the legs? So we already said that if we were given the legs to get the hypotenuse, we would just have to multiply by the square root of 2. So how do you think we would find the legs? You would remove the square root of 2. How? Divide by it. All right. So in other words, we would divide the hypotenuse by the square root of 2. So in other words, from leg to hypotenuse, we would multiply by the square root of 2. From hypotenuse to leg, we would divide by the square root of 2. So, all right. Let's see, Amelia was the last person to talk. So Amelia, pick someone to tell me how to find the first triangle's legs.
I do 7 over There's 7 square root of 2 and divided by the square root of 2.
Good. So what would you get for both legs? 7. These would cancel. You're left with 7 for both. All right, pick someone for the next one. Okay. Good. All right, last one's a tricky one. Elizabeth, pick someone to, or Lizzie, sorry. Pick someone to. Mm-hmm. All right, right. Because what do we end up having to do with that denominator? We got to rationalize it. So we would multiply by the square root of 2 over square root of 2. That would give us 10 square root of 2 over 2, which if we simplify the 10 to 2, that's 5 square root 2. So that's what these would be. All right, so sometimes it's not always going to be a nice, like, square root of 2 next to our hypotenuse. All right. If that happens, you just rationalize the denominator. So for a 45, 45, 90 triangle, again, this is known as a special right triangle. Specifically, if you had a 45, and a 90-degree angle, first off, it is an isosceles triangle because you have those two congruent angles. That means the opposite sides are congruent. So we would call both of these sides A. And then to get the hypotenuse, you would do A times the square root of 2. So this would be your leg, your hypotenuse. So again, if you're going from leg to hypotenuse, you would multiply your leg by the square root of 2. To go from hypotenuse to your leg, you would divide your hypotenuse by the square root of 2. All right. So in other words, guys, if this is a certain type of right triangle, this special type, you don't have to do Pythagorean theorem to find the missing sides. All right, you just have to do this trick, and that's all you got to do. Even if they only give you one side, if you can show that it's a 45, 45, 90 triangle, you can find all the other sides. You guys good? All right. So let's work through these together. So first off, if you only have one 45-degree angle, but you also have a 90-degree angle, that automatically means the other angle is 45 by the triangle sum theorem. All right? So we know it's a 45, 45, 90 triangle. What side type did they give me? Did they give me a leg or the hypotenuse? A leg. All right. So let's call this X and this Y. All right. We know this is a leg. What is X? Is X a leg or a hypotenuse? It's a leg, which means Y is the hypotenuse. All right. So automatically, what should X equal? 6. What should Y equal? 6 square root 2. Good. All right. Letter B. Remember, these two symbols right here mean congruent angles. And remember, the only way that you can get two congruent angles and a 90-degree angle at the same time, they have to be 45 degrees. So, did they give me the hypotenuse or a leg? hypotenuse. So we'll call this X and this Y. So since that's the hypotenuse, the other two are my legs. I would get in the habit of labeling hypotenuse and legs. All right, just so you don't mess up. All right. So if that's my hypotenuse, how do I get my leg? I divide 11 square root 2 by the square root of 2, and I end up with what? 11. So X is equal to 11, Y is equal to 11. Now, yeah. Now, number 2 states, if the hypotenuse of an isosceles right triangle is 20, what are the lengths of the legs? So remember, an isosceles right triangle, automatically it's a 45, 45, 90. It's the only way a right triangle can also be isosceles. And it says the hypotenuse is 20. And they want us to find the 2 legs. How would I get it? Divide 20 by the square root of 2. All right? Now what do I do? Rationalize the denominator, so I multiply the top and the bottom by the square root of 2. So I get 20 square root of 2 over 2. So what's my final answer? 10 square root 2. Because the 20 over 2, that would divide into 10. Any questions so far, guys? All right, simplifying radicals. I know y'all are fully capable of that. So 32, what's 2 factors where 1 is a perfect square? 8 and 4, 16 and 2. I'm going to use the 16 and 2. So if I change this to 16 times 2, what comes out? A 4, because square root of 16 is 4, so this will be 4 square root 2. What about 20? 4 and 5, because one of them is a perfect square. What comes out? 2 square root 5, because the square root of 4 is 2. Now, letter C, we're not actually simplifying the radical. We mainly have to do what? Rationalize the denominator. So I'm going to multiply top and the bottom by the square root of 2. I get 40 square root of 2 over the square root of 4, which is just 2. So what's my final answer? 20 square root 2. Since it's outside the radical, you can't simplify it. It's a coefficient technically. So you only want to simplify what's under the radical. All right, last one. 45, 45, 90 triangle. And they gave me one of the sides. Is that the leg or the hypotenuse? Leg. So let's call this X, this Y. Is X a leg or a hypotenuse? It's a leg. So this is a leg, this is a leg. So what is X? 6 square root 2. Which means Y is my hypotenuse. So how do I find it? Multiply by the square root of 2. So 6 square root 2 times the square root of 2. You just multiply what's under the radical. So this would be 6 times the square root of 4. What's the square root of 4? 2. So this would be 6 times 2, which is 12. So Y is 12. Any questions on a 45, 45, 90 triangle? All right, so make sure that gets glued into your journal. That should go after the one from Monday. That's why I said hold on to the one from Monday. And then you're still responsible for that I can statement. Once you do that, take out your packet and turn to page 5. packet should be out, page 5 of your packet. So today we're going to talk about what trigonometry actually is. It's pretty much a brand new topic. You haven't seen it in anything yet. All right. But essentially, the goal of trigonometry is to find missing sides and angles of a right triangle without having to do anything like the Pythagorean theorem or using a special right triangle theorem. All right. Essentially, you can find the side or angle of any right triangle as long as you're given one side or one angle. All right. Now, so in the last lesson, we talked about similar triangles and how ratios of relatively positioned sides within similar triangles are equal. All right, so that's why we started with similar triangles on Monday, because it does relate to trigonomic ratios. Now, when this gets applied exclusively to right triangles, these ratios now become what we call trigonometric ratios. All right. Now, below you get two right triangles, and they have that acute angle of 35 degrees marked. Now, it asks you to measure all the sides, but for timing's sake, I'm just going to give you the measures. This is 42, 35, 24. This is 55, 45, 32. So if you actually measured that in millimeters, that's what it would have been. Now, take a minute, and I want you to label just the first 6 boxes. So the first 3 columns, so these first 6 boxes. So just tell me what the side lengths are. All right, so take a minute, write that down. Now, what do you guys notice about how they lined up the sides? So in the table, why did they line up the sides the way they did? Or why they order those sides the way they did? What do you notice? Right. So in other words, in the same column, you have the corresponding sides. All right. So BC, its corresponding side is EF. AB, its corresponding side is DE. AC, its corresponding side is DF. All right. Which make these ratios a lot easier to find. Now, I'm going to write out the ratios, and what I want you guys to do is in your calculator, I want you to put those ratios in and then round to the nearest hundredth. All right, so we have 24 over 42, 35 over 42, 24 over 35, 32 out of 55, 45 out of 55, and 32 out of 45. So put all of these fractions in your calculator and then write down the decimal that you get to the nearest hundredth. So that's 2 decimal places. So take a minute and do that for all 6 of them. No, you're not adding anything. Just simplify them. So you just do 24 divided by 42, 35 divided by 42, so on and so forth. And then just write down whatever decimal you get, but round to 2 decimal places. All right, thumbs up if you're ready. One more minute. All right, what'd you guys get for 24 over 42? So as a decimal, 0.57. Sorry, my ears are all stuffy, so you may have said that, but I just did not hear. All right, 35 over 42. 0.83. Is it 80 or 83? 83, okay. All right, 24 over 35. 0.69. 32 over 55. 0.58. 45 over 55. 0.82. We should round up. And then 32 out of 45. 0.71. Now, what do you notice about the ratios in comparison to their corresponding? They're really, really similar, probably off by a couple decimal places. All right. So basically, if the ratios are calculated for the two triangles, should they be equal? That's the question. So should they be equal? So what do you guys think? Should they be equal? Yeah, why? Because they're coming from what? What do we do all day on Monday? Similar triangles. So they're coming from similar triangles, which we know that these two triangles are similar based off of what postulate? Angle, angle. All right. So the ratios should be equal because the two triangles are similar by angle, angle. Thus, the sides should be proportional. They are slightly unequal due to rounding errors when you measure the side lengths. So if we actually took the time and actually measured these side lengths by hand, you would have had some rounding errors. All right? And that's why they're slightly unequal from measuring the side lengths. So if we actually had like an exact measure for all three sides, they would have been equal. All right, but since we were supposedly measuring by hand, which in reality we didn't, but I gave it to you, that's why. So we're going to treat this like they are equal, though, because they are similar triangles. Now, let's say we had a third right triangle, all right, and it's shown to have that 35-degree angle as well as the 90-degree angle. So triangle TRS is what to the other two? Similar because of angle. All right. So now we can find the measures of ST and RT using the similar triangle proportions. All right. So we have RS. All right. They gave us RS. So we're going to use that one in relation. Now we're going to look at the proportions up top and ask ourselves which one or which proportions contain the corresponding side to RS. So up at our table, which ratios contain the corresponding sides to RS? A, B, and D, E. So any one of them that says A, B, or D, E in it, we can use. So we can use these two proportions or these two proportions. All right. So if I want to find ST, all right, which proportion would I use? So in other words, we have to use RS in it, but what order will we do? So will we do ST over RS or RS over ST based off of what we have up here? So in other words, find the corresponding side to ST. So BC and EF. So that means we would have to use these two proportions. And it doesn't matter which one we use. So that means that we're going to do ST over RS, because we're dealing with corresponding sides, and set equal to, let's do the top one, so BC over AB. Now, we already found what BC over AB is. Okay, so I'm just going to plug in what I have for RS. So we have ST over 18, and it's equal to what we already got for BC over AB, which is 0.69. So how would I solve for ST? You could either cross multiply, or the shortcut would be just multiply both sides by 18. All right, so we want to get rid of that denominator. We can multiply both sides by 18. You could have also cross multiplied, got the same thing. It doesn't matter. So ST would be equal to what? To the nearest tenth. 12 point what? 4. All right, so we're saying ST is about 12.4. Now, TR. Which of our ratios, we still want to use RS because that was the definite given value. So we still want to use RS in our ratio. But which corresponding ratio up here contains the corresponding side of TR and the corresponding side of RS? So it'd be ABAC or DEDF. All right. So just for variety's sake, let's use DEDF for the next one. So DE, its corresponding side is RS, so we're going to do RS over TR. and set equal to DE over DF. Now, we already know what DE over DF is, so we're just going to substitute in the RS. So this will be 18 over TR is equal to 0.82. Now, to solve, we would definitely have to cross multiply. All right? So we'll put this over 1. So we would get 18 is equal to 0.82 times TR. So what would I have to do to solve for TR? Right, divide 18 by 0.82. So TR will be equal to what? 21.95, so let's call that about 22 if we round it. So 22.0. Now, the question is, what happens if we don't have a similar triangle to reference? All right, so we found these sides using similar triangles like we did on Monday. But the question is, what happens when we don't have another triangle to reference that's similar to the other? So what I'm going to do is I'm going to pass out the paper. So I'm going to pass out to the back people, just pass it forward. All right, I specifically want you to look at the back. So it's the one that says trigonometry table. Okay, so whoever has an extra one, just pass it to the sailor. All right, did everyone get one? All right, so my question was, what do you think we're going to do if we don't have another similar triangle to reference? What we're going to do is use our trigonometric ratios. All right, so what the trigonometric ratios are is because all right triangles have to share an acute angle measure and are similar to some other right triangle. The ratios of the sides within a right triangle don't depend on its size, but only on the acute angles. All right, so it's actually the angle measure that dictates what the side looks like. These ratios are known as the trigonometric ratios, or just trig ratios for short. And they're defined by their relative positions with respect to the acute angle. We also call this the reference angle. All right, so in other words, it's the angle that we are referencing. So all of these ratios are in reference to angle A. So this right here is our reference angle. Now, occasionally you will see this as theta. All right. All right. So theta is the mathematical symbol to represent an angle. All right. So if you see this sign, this is called theta. And all it does is it represents an angle. That's all it represents. Pretty much. It's the Greek letter theta. So, how this works, you're talking about sine, the sides, in reference to the angle in question. All right, so the first one you should always label is the hypotenuse, which is what side length? AC. It's directly across from our right angle. The other two sides are the opposite side of the reference angle and the adjacent. So remember, opposite means it's across from the angle, adjacent means it's next to it. So which side is my opposite? Nope. BC is your opposite. It's directly across from the angle, not next to it. The adjacent side is AB because it's next to it. Theta just represents an angle. Yeah, you're good. So it represents it's like the mathematical common variable for an unknown angle measure. Now, why did I take the time to label these sides? All right. It's because depending on what side or sides they give you, that tells you what type of ratio you're going to use. So there are three types of ratios that we will use: the sine ratio, the cosine ratio, and the tangent ratio. So you guys know on your calculator, like if you look at your calculator, you see like sine, like sin, cos, and tan, but you never really knew what they were for. This is what they're for. All right. So sine you see as sin, all right, of A. So sin of A, so that's the angle measure. You could also see it as sine of theta. And it's equal to the leg opposite A over the hypotenuse. So in this case, that would be BC. So just to abbreviate, like what they just said, sine of theta is going to be equal to opposite over hypotenuse. Cosine, which we see as COS or cos, although we always say cosine, don't ever say sin or cos or tan, just say cosine, of A, talking about the angle measure, so you can also see it as cosine of theta. That is the adjacent leg of A over the hypotenuse. So in this case, it would be AB over AC. So in other words, to simplify, cosine of theta is equal to adjacent over hypotenuse. The last one is tangent. So tan of A or tangent of A, you can also see it as tangent of theta. That is your opposite leg of A, so the leg opposite of A over the leg adjacent of A. So for this triangle, it'd be BC over AB. So just to simplify, tangent of theta is equal to opposite over adjacent. Now you're probably thinking, oh my gosh, that's so much to remember. There's actually a very easy way to remember this, and you'll probably hear this a lot. SOHCAHTOA. SOHCAHTOA. All right. So all it stands for is sine opposite hypotenuse, cosine adjacent hypotenuse, tangent, opposite, adjacent. Now, if SOHCAHTOA takes a little while for you to remember, here's a very nice saying that can help you remember it. So it's some old hippie caught another hippie tripping on acid. I kid you not, this is how I learned it when I was in high school. Some old hippie caught another hippie tripping on acid. This is what my teacher told me when I was in high school. I've heard it in college, I've heard it everywhere. All right? It's a little bit crass, but you know what? It helps you remember it. So some old hippie caught another hippie tripping on acid. That's how you remember it. So sine, opposite, hypotenuse, cosine, adjacent, hypotenuse, tangent, opposite, adjacent. So some old hippie caught another hippie tripping on acid. SOHCAHTOA. Now, why is this important? All right. Well, this is what we're going to be using for the next 2 days to help us figure out different side lengths and angle measures and things like that. All right. Now, while you typically put this in your calculator, I want you to actually know where these numbers are coming from. All right. So look at that orange sheet of paper that I just gave you on the back side where it has the table. All right. This is what's called a trig table. So how it works is, all right, is that your A value is your angle measure. And then listed next to that angle measure will be the value that you would get if you were to plug into your calculator sine of that angle, cosine of that angle, tangent of that angle. All right. So let's actually go through and find what those angle measures actually are for the ones that they list. Okay. So first off, sine of 35. So if I look at the table, how I'm going to find it is that I'm going to go to 35 degrees. So I'm going to scroll down or look down until I see 35 degrees. So that's right here. And then I want the sine of it. So that's this column right here. So the sine of 35 degrees. So that means if we had two triangles and we did its opposite over adjacent in reference to that 35-degree angle, we would get 0.5736. Is that not what we got previously on the backside page for that first ratio about? So on the backside page, that first column, so right here, is that not what we got about? Yeah, it's about what we got. I mean hypotenuse. I meant hypotenuse. Yeah. So that'd be 0.5736. Now, let's double check that in our calculator. So in my calculator, I'm going to hit my sine key. And I'm going to type in 35 next to it and close the parentheses. Uh-oh, we don't get that. Here's a life lesson for you guys. This is why we don't get that. It's because your calculator's in the wrong mode. Your calculator automatically puts itself in what's called radian mode. Now, what are radians? It's another way to measure angles besides degrees. You will learn all about that in Math 3. But right now, we don't care about that. So, whenever we do anything with trig, you automatically have to make sure that your calculator is in what we call degree mode. All right? So, if you have a TI, this is how you do it. You go up to the mode key, which is right next to the blue second key. So, hit mode. Now, does everyone see, once you hit the mode key right here where it says radian degree? All right, you want to make sure that degree is highlighted. So I'm going to use my arrow keys, scroll down until it's hovering over radian, hit the right arrow key, so it's hovering over degree, and hit enter. Now your calculator is in degree mode, which means that if I put in an angle measure in terms of trigonometry, your calculator will read it as an angle measure in degrees, not radians. No, it's not supposed to go blank. Now, how you get out of this screen, you hit the second button again, and then you hit the mode button. So second quit. And it quits out of it. So now, let's try that again. So I'm going to put sine of 35, hit enter, and now we get what we got on our trig table. Now, if you have a NumWorks calculator, yeah. All right, so your NumWorks calculator is just in your settings. That's how you change it to degree mode. All right. So, guys, especially if you're using my communal calculators, whenever we're doing anything with trig, this should be the first thing that you check every day. All right? Because you never know, my second or third period classes may reset the calculators, because if they reset them, it automatically goes back to radian mode. All right? So this should be the first thing you check in every day. Second mode. All right, so let's keep going. So, cosine of 35. I'm going to go back to my trig table. And I'm going to look at the second column, which is cosine. So right here, it's 0.8192. So that'll be 0.8192. Is that not what we got for our second column of ratios? About. It's pretty close to what we got. All right. For our second column of ratios. And then lastly, tangent of 35. If I look at my table again for 35, here's tangent. It's the third row, which is 0.7002. And again, you can double check this on your own in the calculator. It will give you that. All right. And that is about what we got for our third set of ratios. All right. So these decimals are not just coming from, these decimals are not just coming from nowhere. They're actually coming from what some big rig mathematician way back in the day figured out how to get. All right. And that table is what they found for all of those angle measures. So your calculator has all of that information stored into it, so you don't have to think about it that much. All right. Do I expect you to memorize that table? Heck no. All right. Is it a useful tool to use if you just want a quick reference and not have to constantly put in your calculator? Heck yes. All right. Now, in future lessons, we will be working extensively with that calculator. All right. But for right now, we're just more focused on making sure that you get those ratios. All right? So you gotta be paying attention to what the reference angle is and then label accordingly. All right? So let's do some practice with just setting up the ratios. All right? So letter A of exercise 4. What's my reference angle? R. So in other words, whatever it's labeled next to your trig designation, so sine, cosine, tangent, that's your reference angle. So I'm using R as my reference angle. So my recommendation to you, whatever reference angle you're using, you should automatically go ahead and label hypotenuse, opposite, adjacent. All right, based off of that angle. So which side would be my hypotenuse? 13. Which side would be my opposite? 5. Adjacent? 12. Now, how do I find sine? It's what over what? Opposite over hypotenuse. So sine is always opposite over hypotenuse. So what two sides is that? So this would be ST over TR. So my ratio would be what? 5 over 13. Good. Cosine of R. So we're still finding cosine with R being our reference angle. So cosine is, how do we find it? Adjacent over hypotenuse. So what two sides is that? RS over RT or TR. So what's my ratio? 12 over 13. What about tangent of R? So tangents, how did we find it? Opposite over adjacent. So what two sides is that? So TS or ST, let's keep it consistent, over RS. So that'll be what? 5 over 12. All right, and that's all you're doing for these. You're just writing out the ratios, and we're going to leave these as fractions. Now, tomorrow you'll see where these come into play with actually finding the missing sides and stuff, but for right now, I want to make sure you have a solid understanding of how to get those ratios. Now, D through E, D, E, and F. If you notice, the reference angle changes. We're now referencing which angle? T. So we're going to label accordingly. So T is my reference angle now. The hypotenuse stays the same. But what's my opposite now? 12. What's my adjacent now? 5. So I would either label that in a different color or maybe box it so you know that it's with a different reference angle in mind. So sine of t, we're still doing opposite over hypotenuse. So what two sides would that be with angle t in mind? So what's my opposite? What's my hypotenuse? So it'd be RS over what? What's my hypotenuse? What side? TR. So that would be 12 over 13. What about cosine of t? We know it's going to be adjacent over hypotenuse. So what two sides is that? ST and TR or RT, doesn't matter. So what's the ratio? 5 over 13. And then lastly, tangent, that is opposite over adjacent. So it would be RS over ST, which is 12 over 5. So if you notice, guys, depending on what angle they have you reference, the ratios can change. So you need to make sure that you pay attention to what your reference angle is. All right? And again, get in the habit before you do anything with trig, whatever the reference angle is, go ahead and mark which side's your hypotenuse, which side's your opposite, and which side's your adjacent. It makes your life so much easier. All right? Because what's going to happen is that tomorrow when we find missing angles and missing sides, you're going to have to decide which trig ratio to use based off of the information they give you. All right? All right. Now, so what should the sum of the two acute angles be? It should be 90 degrees. So that means what type of angle pair are they to each other? They're complementary. Now, what seems to be true about the sine and cosines of the two acute angles? All right, so between R and T up top, what's true about the sine and cosine of them? They're the same ratios, they're just flipped. Same ratios, but switched. Now, why do you think that makes sense given how the ratios are defined? So first off, wouldn't the hypotenuse stay the same for both? That won't change, right? Right, the hypotenuse doesn't change. The only thing that changes is opposite and adjacent, which, you only have two sides to play with that. So that makes sense that they would be flipped. All right. So hypotenuse stays the same for both, but opposite and adjacent switches based on the reference angle. All right. Any questions on this? All right, so your homework for tonight is pages 7 and 8. I'll check the homework from Monday tomorrow. All right. So again, my recommendation is use your trig table for right now, especially if you're doing it at home and you don't have a calculator. Use your trig table for right now to find these angle measures. Also, if you do want to use a calculator, you can always use Desmos. Desmos, you can also switch into degree mode. You just have to go to that little wrench key and then it'll be right there. So guys, real quick, just look up here. So if you were using Desmos at home, all right, what you would do is that you would hit the little wrench key in the top right corner, scroll down until you see radian degrees, and then just click on degrees. And now it's in degree mode. Yes, ma'am.
Can you tell us the that triangle for homework?
Oh, yeah. Hold on. Okay, so the lengths for, what was it, number 1? So I'll give you the length. So it's 60, 26, and 65. Nope, I think that's it.
Would this angle just be 67 too?
No, that angle would not be 67. It'd be whatever 90 minus 67 is. All right, guys, so you got about 15 minutes, so you can probably get a little bit done. I just gave it to you. Oh, you would have to use a ruler and measure it. Yeah. It's like what we should have done in the first example that we did, but I'm too lazy to make y'all take out a ruler. So I really only care if you can actually get the ratios correct. So again, use your trig table, especially for number 2, and then double check yourself in your calculator. But I need you to be able to use a trig table. So make sure you understand how to use the trig table.